All right. So yes. So now part A and part B should not be challenging, but I want to make sure that you understand one thing. I want to reiterate this from last class. How do we determine Rate's law? We can only determine Rate's law from experiments. Okay? And you understand why I keep saying this. So this is the experimental data. I think you did this in your lab as well, right? So what are we looking for here? We're looking for a straight line. And 1 over concentration of NO2 is a straight line, and the other two, they're not. So we are seeking for a straight line. That's how we know it's a second order. And so for part B, you know it's going to be this. So this is the fact, all right? This is the fact. We found out the rate law from the reaction, okay? From the experiments. We got it. So that brings us to part C. What we are seeking in part C is, we are now proposing mechanisms, and we want to know if they are true or not true. Well, how do we know? Well, the Rate's law from the proposed mechanism has to match with our fact. Okay? If it doesn't match, then the proposed mechanism, it's not going to fly. So now, and I hope this would also give you a little anticipation of what you are looking for here. We're looking for the slow step right here, which is step 1. We look at the 2 reactants right here. We can now write the rate law based on this particular rates determining step, and we say, hey, that's the rate law from the slow step. Hey, that's exactly the same from what we determined experimentally. So this is a possible, it is a consistent, this mechanism is consistent with our rate law. That's a key word, consistent. This mechanism is consistent with our rates law. It is possible. We're not saying it is the mechanism, but it is possible. Okay. And part 2, we're like, hey, go ahead, try this out. And we look at the slow step again, and we say, well, what's the rate law? The rate law is going to be rate is equal to K times N2O4. And when you do this, I hope you know what the question is testing you. The question is testing you if you know that intermediate cannot be expressed in the final rates law. The question wants to see if you understand that, hey, there's an equilibrium that involves the intermediate. So the key right here is N2O4 or NO2 squared. It's practically the same as N2O4. Therefore, you can replace this with NO2 squared. And we say, hey, that's exactly the same as what we determined experimentally. So we say, hey, you know what? The second mechanism, it's also possible. Okay? And we just stop right there. That's all we're asking. Are they possible? Are they possible in this case? All right, now, before you go, I want to show you one last question. Okay? Now, this question is by far the, I want to say the trickiest. The trickiest question, or the I don't want to use the word trickiest actually, but you got to be very careful with the data. Okay. Now, ask yourself, if you look at these numbers and they said, hey, go ahead, determine the rate law, what would you do as your first step? Are you thinking about like doing this, like subtracting concentration, subtracting time to get the rate? I would think about it too. And then I hope you also realize a problem, and that is, if you do that, all you're calculating is the average rate, not the rate at that particular time. So don't go there. The rate is equal to what? K N2O5 to the what power? Square? Y square. Well, but that's the overall reaction. Okay, that's why I said last week and earlier today, you cannot use the coefficient in the overall reaction to write your rate law. You may only use the coefficient of the elementary step to write your rate law, like these elementary steps right there. Okay? If they say, hey, step 1, step 2, that you can use the coefficient. This one you cannot. So let me tell you what the order is. Let me go ahead and highlight some data and see if you can sniff out the key, the magic behind the data. What do you see here? Any kind of pattern or consistency? Divide by half? 100 seconds for each ray? So what it does is that it inserted this row right here to throw people off. So, but if you look at this, these 4 rows, you'd be like, hey, the half-life, it's here. What's half-life? 100 seconds. Because you can see it's going down by 50%, right? So that's why I said, well, it's kind of tricky because it's not telling you these facts up front. And you need to say, oh, whoa, that's sneaky. Well, it won't be because, again, when we have half-life, it's going to be first order. And we are not going to ask you something beyond the scope of AP chemistry. That's how you know it's first order. Because again, for first order reaction, the half-life does not change when the reaction changes. But for zero order and second order, the half-life would change when concentration changes. Okay? For first order reaction, the half-life is consistently the same. So that's why you know it's the first order. And the rest is pretty straightforward. Calculate the value of K. How do you calculate the value of K in this case? Plug in what to where? Okay? Because I'm worried that you might be thinking like, oh, do I plug in the rates to find out the K? Do I plug in concentration to find out the K? Well, there's no rate. It's not given. But it's first order. And that's how you know you use the 0.693 divided by half-life to find out the K value. So basically it is 6.93 times 10 to the -4, -3. Okay, that would be the K value. Sorry, that would be the K value. All right, what's the concentration of N2O5 at 500 seconds? I just want to hear what you would do to find out this concentration. I'm not too worried about the answer, but what do you do to find out, hey, what's going to happen at 500 seconds? I think there are 2 ways you can do this. I want to hear what your thought process is. Mm-hmm. Yeah, because you know the half-life, right? So that means you can just divide by two times. You can do that. Or the other way is, well, if you know it's first order, that means what? You can use the integrated rate law. You've got the K value earlier. You can do that as well. Okay? And the initial concentration is 0.1. That's given to you. So there are two ways you can get the answer for part C. You can just go ahead and divide by two more times, or you can also say, hey, guess what? The half-life is 100 seconds, right? So the initial concentration is 0.1 molar, and we're going to multiply it by half. How many times? 5 times, because if the half-life is 100 seconds, and there are a total of 500 seconds elapsed, then there should be 5 half-lives. You can also do this to get your final answer. So what I want to make sure is that whenever you see the word half-life, I want to make sure that you know what gates are wide open for you to find out the answers. Okay, and again, half-life, it's only related to first order reaction, at least for us in AP chemistry.